Hello students, welcome to SOURAV classes. Today we'll be solving the question paper, the maths question paper of TIFR 2017 part 1. So let's start by solving question number 22. We have solved from the question numbers 1 to 21 in the earlier videos. Today we'll be solving question number 22 and question number 24 from this paper. So let's begin. It has been said that P is a monic non-zero polynomial of even degree, okay, and K is greater than 0. Then we have to find whether the function Px minus K e to the power x has a real 0. We have to check whether this statement is true or false. So let's begin. Let us assume that Qx is a function which is equal to P of x minus K e to the power x. We have taken a function Qx. So in that case, Q of 0 is equal to P of 0 minus K, or Q dash x is equal to P dash x minus K e to the power x. And if Q dash is equal to 0 implies P dash x minus K e to the power x is equal to 0 implies P dash x is equal to K e to the power x. This is, if Q dash x is equal to 0, then this is the condition that will come to. Now we know that Px is a even degree function. So if we differentiate, it comes at degree, it falls down a degree, and in that case P dash x will be an odd degree function. Now if Qx is equal to 0, this implies P of x is equal to K e to the power x. Now as x tends to infinity, P of x minus K e to the power x tends to minus infinity. This implies that P of x is less than, much less than K e to the power x eventually. Similarly, as x tends to minus infinity, we'll see that P of x minus K e to the power x tends to infinity, and this implies that P of x is much greater than K e to the power x eventually. So by intermediate value theorem, we get that there exists x naught such that P of x naught is equal to K of x naught, or in other terms we can say that Q of x naught, which is equal to P of x naught minus K e to the power x naught, is equal to 0. And so we can say that this function has a 0, and such this statement is true. Now let's solve the next question, which is question number 24. In question number 24, it has been said that A is an n cross n real matrix whose eigenvalues have absolute value less than 1. Then we have to show that for any vector v which belongs to Rn, this condition is satisfied. Let us begin by solving the question. Let me erase this portion first. Okay, now let's begin. We can consider some general values, general for matrices A and some general vector V for the simplicity. of the problem. Let A is equal to, let A be an n cross n matrix which is of the form 1 by 2, 1 by 2, 1 by 2, 1 by 2. It is n times, it goes n times, and we're only concerned with the eigenvalues over here, so it is something like that. It goes on, and here it is 1 by 2. It is an n cross n matrix, and we can take another a vector v which is of the form 2, 2, 2 n times. So basically it is an n cross 1 matrix. Okay, so now let's begin. We've been given the condition. A condition has been suggested to us where it has been said that is always, is it less than equal to or less? Let me check once more. Okay, it is less than equal to, it is less than equal to. So in that case we our structure will come down to 1 by 2, 1 by 2, 1 by 2, 1 by 2. Here we can see that the eigenvalues are all, less than, the absolute value of these eigenvalues are less than 1. This is 2, 2, 2. This is V. And when we want it comes down to n into n minus 1 to n. And once we solve it, we get n into 2 square is less than equal to n into n plus 1 by 2, and this implies that n is greater than equal to 7. So only if n is greater than equal to 7, then this will hold true, then this condition will hold true. But if n is less than 7, then it will be false. So for any n cross n matrix, this condition is not entirely satisfied. Suppose for n less than 7, this is false, and for n greater than equal to 7, this is true. So the entire statement is false. So today we have solved question number 22 and 24 from the TIFR paper. We'll be solving the next questions in the upcoming video. Thank you and all the best.